Alright, hey AP Chemistry, this is going to be a major video for the bulk of understanding of Chapter 10. In this video, I'm going to talk about how we could go from structure to figuring out shape and geometry, and then hybridization. And I'd like to summarize all of what you could have read on this one page in this table. Okay, now just as an aside note, on page 436, which is table 10.1, your textbook does a pretty awesome summary with examples of all of the different types of shapes and geometries of all of the Lewis structures that we could be drawing. I'm going to quickly go through those and then also connect that to hybridization. Now, I don't normally like to do shortcuts or summaries like this, but because of a crunch for time, I'd like to just summarize how you could figure out the shape of molecules. So, for AP Chemistry, there are either going to be anywhere between 2 and 6 electron-dense areas, or that means bonding, or some type of lone pair around a central atom. So this number is how many things, I like to refer to number of electron-dense areas as things, is how many things are around my central atom. So for this first one, if I have 2 things that could be a bond or a lone pair, the parent, or the electron pair geometry, is going to be linear if it's 2 things. And I call this kind of like your parent shape. Right? It doesn't matter if it's a lone pair or a bond, it's just in general, everything attached to the central atom makes a linear shape. And if there are no lone pairs, like I said, it would just be linear, right? So I'm going to talk about electron pair geometry versus molecular geometry. Molecular geometry gets changed because of lone pairs. Okay? And that's because this is known as valence shell electron pair repulsion theory. That is, electrons in bonds want to give themselves as much space as possible, and that spacing gives a certain type of shape, right? So electron lone pairs tend to repel each other, right? Electron pair repulsion theory. All right, so now let's talk about if I have some lone pairs versus non-lone pairs, right? So if I have 3 things around my central atom, let's say it doesn't matter what those 3 things are, the overall parent shape, or we call it electron pair geometry, will be trigonal planar, right? So if there's no lone pairs, trigonal planar. So these 2 columns are going to be equal. I don't know if you see that. If I have 1 lone pair, it looks like a trigonal planar shape, but the shape of the molecule, which we're going to call the molecular geometry, is bent. That is, if I cover my lone pair, the shape of the molecule makes a bent shape. So when I talk about molecular geometry, I'm talking about if I cover the lone pair, what shape do the molecules make? So covering LP, and LP stands for lone pair, by the way. And that's like a pair of electrons that are not bonding, right? Covering up lone pairs, what shape? That is the molecular geometry summarized. Electron pair geometry is everything. What shape does everything, lone pairs or bonds, make? Okay? If I have 4 things around the central atom, and again, when I say things could be lone pairs or bonds, right? So things are either lone pairs or bonds. Okay, that's just a summary there. If I have 4 things, typically the parent or electron pair geometry is tetrahedral, we call it, 4 things around the central atom. If there is 1 lone pair, the shape that my molecules make is known as trigonal pyramidal. If there are 2 lone pairs, and if I'm covering both of them, you kind of see it, the shape that my molecule makes is bent. And an example of a tetrahedral electron pair geometry with 2 lone pairs is water. This is what water looks like. Water has the bent shape, which is also a tetrahedral electron pair geometry. Now, how can I distinguish between this bent and that bent? Well, the only difference is the amount of electron domains or electron dense area or things. This bent is a trigonal planar bent. This bent is a tetrahedral bent. Okay? Now, if I have 5 things around my central atom, That's going to be trigonal bipyramidal. So no lone pairs, trigonal bipyramidal, right? I can't cover any lone pairs. If I have one lone pair, it's known as sawhorse, right? And why do you say it looks like a sawhorse? Well, it means, if you remember, if you've ever been on the playground, right? The sawhorse is that thing where it kind of keeps you like this, and then if one person's on one end, it goes down, and one person's on the other end, it goes the other way. That's known as a seesaw or a sawhorse, and that is the shape that the trigonal bipyramidal makes with one lone pair, right? And this is where one person would be sitting and the other person would be sitting, and it would be going back and forth. Sorry, this one. We call that sawhorse. If there are two lone pairs, we call it T-shaped, right? The molecules would just make a T, right? So if you could see it, this is the T shape that the molecules make, right? So if there are 5 things and 2 lone pairs, it's T-shaped. If there are 5 things and 3 of those things are lone pairs, it is linear. And that's typically I3 minus, right? It looks like this, I, and the central atom I has 3 lone pairs around it, okay? So this makes a linear shape. So if there are 5 things around the central atom and 3 of those things happen to be lone pairs, right? You see that, for some reason, 3 lone pairs, it gets a linear shape, okay? And the last set of shapes that we will worry about is octahedral. That's if there are 6 things around my central atom. So if there are no lone pairs, it's octahedral. If there is one lone pair, it is square pyramidal. I don't know if you can kind of see that with me blocking my thumb here. Square pyramidal. Some people tend to put they drew it this way. They put the lone pair on the bottom, so it looks like this. That's okay too, right? Same idea, as long as you identify that as square pyramidal. If I have 2 lone pairs, then it's just square planar. I don't know if you can see me doing that. Square planar. If I have 3 lone pairs, I'm T-shaped. And now this T-shaped would be an octahedral T-shaped, and this T-shaped would be a trigonal bipyramidal T-shaped. And then finally, if I have 4 lone pairs around the central atom, it would be linear. And again, this linear would be an octahedral linear, whereas this one would be a trigonal bipyramidal linear. And again, and how do I use these names? You have to either be asked for electron pair geometry, which is any one of our parent geometries, linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. These are our basic parent electron pair geometries. What do all the things around the central atom give me as my shape? And then my molecular geometry is what are just the atoms in that molecule giving me the shape of. So for example, this would be water, right? Water is bent. Although there are 2 lone pairs, and let's say that my black markers are my 2 lone pairs here, although there are 2 lone pairs and they give me kind of like a tetrahedral shape, the black doesn't really get counted as a shape of the molecule. The molecule is just what are in the atoms. And so that's just how we distinguish between what is molecular geometry and what is electron pair geometry. Okay? And then the last thing I'll kind of summarize is hybridization here. I like to do shortcuts with hybridization using the number of things is equal to letters, which is my things is equal to letters. And I'm going to explain what that means in a moment. Okay? Now, on page 458, there's a nice summary of your hybridizations. If you read what a hybridization is, or even think about what the term hybrid means, it's a combination of orbitals, atomic orbitals to be exact. When orbitals overlap, you get bonds, right? So you have an overlap of the s or the p or the d orbitals, or even sometimes f orbitals, but we don't talk about that here. If you have an overlap of those orbitals, you have bonds now. And so just in case hybridization does come up, hybridization is going to look like this. If I have 2 things around my central atom, I use 2 letters, which is sp. If I have 3 things around my central atom, that's going to be sp2, which is written as SPP, right? sp2 is s and 2 p's. That's 3 letters. If I have 4 things around my central atom, that's going to require 4 letters. That's sp3, hybridization of orbitals. If I have 5 things, that's going to be sp3d. And if I have 6 things around my central atom, that's going to be sp3d2. Okay? Now, that is really all I want you to know how to do with doing hybridizations. These will be our 5 different types of hybridizations that we could talk about, although there has been a lot of talk and rumor that sp3d and sp3d2 are not really reliable hybridizations anymore. And so for AP chemistry, you really should only need to know sp, sp2, and sp3 hybridization, right? And so if there are 2 things, doesn't matter if it's lone pairs or not, 2 things around the central atom, sp. 3 things around the central atom, sp2. 4 things around the central atom, sp3, and that's either tetrahedral, trigonal pyramidal, or bent. If it's sp2, it could be trigonal planar or bent. If it's sp, it's linear. So the shape is not dependent on the hybridization. The hybridization can give you either of these shapes, right? So I could have 5 things around the central atom. It doesn't matter if it's 3 lone pairs, 2 lone pairs, or 1. The hybridization would still be sp3d. I could have 3 things around the central atom, and it could be 3 atoms, or it could just be 3 bonds, or just a 1 lone pair and 2 bonds. It's still going to be sp2. Okay? Now let's put this idea to an example, and I'm going to keep this off to the side. Right? So let us determine the VSEPR geometry for NF3. So I'm going to draw the Lewis diagram for the molecule NF3, and now I'm going to kind of shortcut it and put the answer here already, but you could watch one of my previous videos and follow the steps on how I draw NF3, but NF3 is going to look like this. F, 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 lone pair, and these all have lone pairs too. And now, I'm still not intentionally making the shape of NF3 like this, but kinda subconsciously am, because I already know what the shape is because I've studied this forever, right? So now it says, draw the structure. Now here's my structure. Determine the number, step 2 is determine the number of bonding pairs and lone pairs of electrons around the central atom, right? So my central atom in all this is N. For N, there are 3 bonds and 1 lone pair. That's 4 things in total. All right, so that's that things that I was talking about on this table over here. What are my things? 4 things. I know I'm going to be over here somewhere. Okay? It says use VSEPR to determine the electron pair geometry for that number of electron pairs. Well, like I said, for 4 things, the electron pair geometry is tetrahedral. Tetrahedral. And I'm going to put on the side that since it's tetrahedral, the hybridization, doesn't matter if it's lone pairs or bonds, is going to be sp3. To determine the molecular geometry, cover up any of the lone pairs, right? So I'm going to try and do that. And rename your shape. If there are no lone pairs, the molecular geometry is equal to electron pair geometry. If I cover this up, what shape does this kind of make? Well, if I don't know that off the top of my head, or if I didn't draw it the correct way or know how to draw them, I'm going to look at this table, or even the table that you have in your textbook on page 436. So I have 1 lone pair, which is under my 4 things. So 1 lone pair, that looks exactly like my NF3. That's going to be trigonal pyramidal. Trigonal pyramidal. All right, and this is using the table. I use this table, or I would really urge you to copy the table that's in your textbook on table 10, that's on page 436. It would help you remember and memorize the different shapes. And then you might want to add in table 10.3 to the side with the SP, SP2, SP3, SP3D, and SP3D2. Okay? All right, so that is how we determine the shapes. I'm going to do one more example, and then I'm going to go and talk about polarity. So one more example, I kind of skip-fibbed this. Oh, by the way, this handout will be found on the Google Classroom. I've shared it as a Google Doc. If anybody would like a hard copy to use for the future, just let me know. But again, it's not mandatory that these are kind of notes that you're going to be doing on your own, okay? So let's do the Lewis structure for PF5, okay? So I'm going to quickly kind of do P has 5 valence electrons, F has 7 electrons, and then there's 5 of them. That means that there's 40 electrons. PF F5. Now, I'm going to start drawing it arbitrarily like this, right? So 40 electrons, and I just used 1, 2, 4, 6, 8, 10 electrons for the 5 bonds, and then I'll do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. And I use all 30 of those electrons to give my non-central atoms an octet. Do you see how quick it was for me to make that structure? There are no electrons left, so I don't need to put any on the central atom, and everybody has an octet, and P is able to have over an octet because it's in period 3 or lower. Period 3 is for P, so it can have over an octet. And if you really want to know the reason why, once you get into period or row 3 on the periodic table, you're able to open up d orbitals, and d orbitals can hold more electrons. Okay, so here's my structure. Determine the number of bonding pairs and lone pairs of electrons around the central atom. Well, there are 5 bonds. So 5 things, I call it. 5 things. There are no lone pairs. Now, if I were to do it off the top of my head, 5 things I know has a parent or electron pair geometry of trigonal bipyramidal. Trigonal bipyramidal. And if I want to draw this PF5 without all these lone pairs correctly, it should look like this. P, 1, 2, 3, 4, 5. That is the nice way of drawing trigonal pyramidal. And they call it trigonal pyramidal is because you have bipyramidal is because technically you make like these 2 pyramids bipyramidal, and you have this triangular shape in the middle. Okay, so this is trigonal bipyramidal. And there are no lone pairs, so the molecular geometry is also trigonal bipyramidal. I didn't read the steps, but you could read the steps on the side. It says, determine the molecular geometry, cover up any lone pairs. There are no lone pairs. And then if I want to do hybridization of this would be sp3d. How did I know that? There are 5 things. I need 5 letters. So sppd. 1, 2, 3, 4, 5, which we call that sp3d. Right? And just a side note, remember there is 1 s orbital, 3 p orbitals, and 5 d orbitals. So technically, if I was going to go crazy, I could have some weird hybridization that's sp3d5, and that would have 9 things around the central atom, but we don't talk about that in the scope of AP Chemistry. The last thing that I will talk about is I'm going to go back to NF3 here, okay? Right, so I'm hoping that you were able to follow on how to get shapes and do a quick shortcut on hybridizations. Let's talk about molecular polarity now. Okay. Now, if you remember in a previous video on whether or not bonds are polar, nonpolar, or ionic, you look at the differences in electronegativity. I'm going to tell you right now that I have dipole moments that go from the N to the F. F doesn't matter. Doesn't matter who F is bonded to unless it's itself. Does not matter who F is bonded to. F is the most electronegative element, fluorine. So dipoles always go towards it. And remember, it goes from less electronegative to most electronegative. And that's our delta plus and our delta minus. All right, that's just a quick recap in a previous video. So what's going to happen is I'm going to have these delta minuses at the end, and I'm going to have a huge delta plus on the nitrogen with a lone pair. Now, if I have all of these dipoles and nothing is getting canceled out, right, and I have a lone pair on the central atom, this is definitely a polar molecule. This is all sorts of polar. There's a lot going on. There are dipoles that are going everywhere, and there's a lone pair on the central atom. Okay? So this is going to be a polar molecule. Let's look at PF5, though. Yes, we have fluorine again, so I have all these dipoles that are going towards fluorine. Okay? However, all of them are going in opposite directions, right? So it looks like I have an F going up and an F going down. And it looks like I have an F dipole going this way, and then I have a dipole going one way this way and one way that way. If you look on page, I forget what it is in your textbook, something about vectors. They talk about vectors. I do not need you to calculate vectors. This is on section 10.5 in your textbook. Page 442. Page 442, they talk about vectors. Now, you don't need to calculate vectors, but what you do need to know is that if I have a dipole going in one direction and I have a dipole going in the complete opposite direction, they cancel out. So dipoles cancel here. So this is a non-polar molecule. Okay? So that's a crash course on differentiating between a molecule that's polar and non-polar. Some common molecules that can be polar or non-polar. Let's talk about water. I mean, we all know from maybe biology or just in life that water is a polar molecule. Why? Lone pairs on central atom. So I can't really cancel that out. Also, the dipoles all go in the same direction. Dipoles in same direction. So there's not going to be any canceling out of dipoles with vectors, okay? But what about CF4? There are all of these polar bonds, right? So look, it has polar bonds. There are all these polar bonds, right? And there's no lone pairs, right? So this is CF4. This is H2O. No lone pairs on CF4. All of the dipoles go in opposite directions. All dipoles go in opposite directions. And they're all the same, right? They're all a CF dipole. Right? All of them are the same. This is going to be a non-polar molecule. It has polar bonds. There are definitely polar bonds, but overall, all of those dipoles, the different ends, the positive, negative ends, cancel out. So I get an overall non-polar molecule. And you could read more about that in section 10.5. Just one last thing. What if I didn't have symmetry or if I didn't have equal dipoles? If I had something like CH3Cl, right? And this was shown on a previous page before. Okay? I'm definitely going to have dipoles, right? And some of the dipoles slightly go a bit towards carbon. But like, we don't really... This is not really not really polar. Between carbon and hydrogen, it's not a polar bond, so like there's no dipole. But between carbon and chlorine, there is definitely a polar bond. Okay? However, this was dipoles look like they were canceling out. This might look like dipoles are slightly canceling out. However, this is not symmetrical. This is a CCl dipole. This is a CH. Even if it was not, what if it was CF3Cl, right? So if I draw Cl and then F, and I get all of these dipoles are not the same. A CCl pulling is not the same as a CF pulling. So either of these are going to be polar molecules. So this whole canceling out, this is the vector canceling. This whole vector canceling out of a dipole has to do with the same elements. If I have a different element in there, these are automatically going to be polar. Okay? Something like CH4 or CB